multiple input, multiple output systems, that is MIMO systems, that do give better capacity and performance, right? So we will start with this first part, that why do we go for MIMO implementation for future generation. In fact, this MIMO communication, MIMO systems have already been implemented for 4G systems, right? So that is LTE or LTE advanced standards. So they are already supporting MIMO systems up to 8x8. That means 8 antennas at transmitter and 8 antennas at the receiver. So that also we will come to when we discuss 4G and 5G specifications. Okay. So this is how advancement of wireless technology took place. So in the beginning, it started with analog modulation schemes. Okay, so when we talk about wireless technology, then we have to discuss about modulation schemes, right? Because it is modulation schemes basically translate our practical signals to higher frequency levels. And so we have analog modulation schemes as amplitude modulation, phase modulation, frequency modulation, and we have quadrature amplitude modulation, which is a mixture of amplitude modulation and phase modulation, right? So these modulation schemes, or we can say that analog systems, they were implemented into first generation of wireless technology. Then digital modulation schemes were developed, and this was basically supported by the digital era, that digital electronics developed, and the IC technology, these technologies and digitization that of the message signals, that helps in having those digital communication systems, right? So here by digital communication systems we mean the modulation schemes, they will remain almost the same in analog and digital systems, but the only change difference is at the message level. If message is analog form, then we call those modulation schemes as analog modulations, and if the message is in digital form, then we call those systems is digital modulation schemes. Okay, so it is although there are certain other differences, but the basic difference is at message level. Okay, message itself is digital, then we call it digital modulation schemes, and the corresponding modulation scheme name, it is uh, now considered as shift keying, right? So AM becomes amplitude shift keying, phase modulation becomes phase shift keying, frequency modulation becomes frequency shift keying, and we also have quadrature amplitude modulation, that is the common name. Okay, but then these modulation schemes, they are fine up to we are doing broadcast, right? So because when this wireless communication began, the initial systems that were developed, they were broadcast only, right? So radio broadcast or TV broadcast, that is what we see. But then when telephony came, then we need to do multiple access also, right? Because we have multiple users and we have limited spectrum. So how to accommodate multiple users, that is through multiple access schemes, and commonly non multiple access schemes are time division multiple access, code division multiple access, and frequency division multiple access, right? So through further improvement, that was through diversity schemes, and then MIMO systems came into picture for certain to overcome certain limitations in diversity schemes. Okay, and then different variants of MIMO systems were also proposed, and in that we will discuss some of the MIMO systems which are proposed to be implemented into 5G systems, right? Fine. So next comes the technology generation timeline. So let us see this. We'll compare 3G, 4G, and 5G. That is what the current generation has seen. So 3G, it was started developing from 1985. Okay, and the group, that is International Mobile Telecommunications 2000, that started discussing about implementation of 3G systems for basically high speed internet connectivity. right? So it started in 1985 and the first release was in 2000. So we can say that it took 15 years to develop 3G communication protocols and standards. While if we consider this 4G, right, so that is LTE and LTE advanced standards, the vision, the first proposal for getting standardizations for 4G was in 2003, and then the release was in 2012. While for 5G it is known as IMT 2020. That means its first release is planned in 2020, right? So and it was started in 2015. So if we see 3G, it took 15 years to get standardized. 4G, it took 9 years to standardize, and 5G, it is planned for standardization into within 5 years. So not only the technology generation is growing, but the rate at which we are going into new standards, that also is increasing. Okay. So just like that, mobile telephony, that also is growing with these generations. Okay. And the first generation, it was analog systems based communications, and that when we consider mobile telephony especially, then we divide our geographic area into cellular structures. Okay, so cellular structures, then each cell will be allotted certain frequency bands, right? So in those frequency bands, we can use frequency reuse, handoff, roaming at different kinds of situations. So frequency reuse, it will actually increase the spectrum efficiency, right? Because one cell, it is allotted some set of channels, right? Some After certain distance, another cell can also be given the same set of channels. So within one particular spectrum, it can be, the frequency can be reused at different locations, so that interference will not be there. Okay, or even if interference is there, it will be limited and it can be handled properly, right? So then since it is mobile telephony, user can change from one cell to another. Okay, so one cell to another cell, nearby cell, it will not be having the same set of channels. So how to take care of this? That is handoff, right? And nowadays, what system we have is, one particular state is having some certain licensed band. Another state, it will have different license band. So it is telecom circle. So circle wise licensing is there. So when a user moves from one center to one circle to another circle, it goes into roaming, right? So this kind of functionalities have been added into mobile telephony. And this GSM, CDMA, these were the standards for 2G. WCDMA standard was for 3G. Then LTE and LTE advanced, this was standard for 4G. And 5G, it is still under standardization. So let us wait for 2020. That is when the first release of standards would has been planned for 5G technology, right? So now let us see how this digital modulation schemes have advanced, right? So in digital modulation scheme, we will just take a brief overview. I hope that basic digital communication course all of you are aware of. Okay, so what this signal as a BPSK modulation scheme, it can be represented as this A cos 2 pi fct plus I pi, right? I pi, because it is only two possibilities, right? This I, it can be 0 or it can be 1, right? We will see for Emery PSK also, that is MPSK. Okay, so this is how the signals are represented. So S0, it is positive, that is A cos 2 pi fct, and S1, that is negative minus A cos 2 pi fct, right? So that constellation, it is represented into vector form. When the signal is represented into vector form, we can draw its constellation points. Okay, so this is binary form. of phase shift keying, and when we go for emery form of phase shift keying, so this constellation diagram that is shown is for m is equal to 8. Okay, while this signal representations, right, so they are in general. So if it is m is equal to 8, then every symbol, every constellation point will take 3 bits at a time for transmission. Okay, so this actually, this 3 bit at a time will improve bandwidth efficiency, right? Because within a certain time we were earlier transmitting only single bit. If we consider bpsk, when we consider 8 psk, m is equal to 8, we are transmitting 3 bits at a time. Okay, so how this improves bandwidth efficiency, that is already seen in our basic courses. Okay, so that we are not going to discuss now, but what we'll see is, see, because this is the points, these are fixed points when there is no noise, and this shows us how the signal points, constellation points, are affected by noise. Okay, so this in this case, this black dots, okay, these black dots, these are actual signal points. Okay, and what happens to these signal points when different magnitudes of noises are added? Okay, so this magenta color, that is a kind of pink color, that shows the noise which corresponds to SNR of 30 dB. Okay, so that is SNR of 30 dB, while this blue color, it shows the points when SNR is 20 dB, and red colors, they are when SNR is 10 dB. Okay, so we can see that when the Gaussian noise, which this noise we have considered is Gaussian noise, when Gaussian noise is added, see, when it is 10 dB, or when the SNR is 20 dB or 30 dB, we can still decode these symbol points almost correctly, right? Because we can still differentiate these points. But when it is red, right, so some of the points, let us consider this pair of these 2 points. So in this case, if some point is corresponds to this, but because of noise it goes nearby this point. Okay, so what we do at the detection point at the receiver is we see the Euclidean distance between the point which is received and the actual point. So if the point, actual point, the received point is away from the actual point, then it will be detected incorrectly. Okay, and what happens when we go for higher order modulation, right? So when we go for higher order modulation, we can see here, see, this is quadrature amplitude modulation. So when we go for higher order modulation schemes, what we will get is, number one is more number of constellation, more number of bits per constellation point. Okay, and the other thing is reduced distance. Okay, so we can see that this is the constellation point for 4 QAM, and this is the constellation diagram for 16 QAM, right? So in 4 QAM and 16 QAM, in this case, whatever diagrams we have shown, it shows same distance between 2 points. See, this is 1, this is -1. So if we consider these 2 points, it is, distance is 2. This is -1, this is 1. If we consider these 2 points, the distance is still 2, right? So the same distance is kept in this case also, right? See, this +1, -1, so this distance between these 2 points is 2. So these two diagrams, they show the constellation points keeping the same minimum distance between two constellation points. But then what will happen is, see, in this point, see, if these 4 points, as far as these 4 points are concerned, we don't have any problem, because these inner 4 points in this constellation and 4 points in this constellation, they are having the same energy. right? Because when we consider energy from constellation points, it is the squared distance of point from the origin. Okay, so this is the origin. So from origin, if we consider squared distance, then energy is same for all 4 points that are inner in inside of the constellation in this, right? But if we consider this point or this point or any of these points which are on the periphery in 16 QAM, they are at larger distance from origin, so their energy will be more. So if we keep minimum distance as same in both the constellation diagrams for lower order modulation scheme and higher order modulation scheme, then we will end up with transmitting more energy, which is also not a very good idea. While if we consider same average energy in both the constellation points, then what will happen is the distance between two constellation points will get reduced. And when distance is reduced, we will end up with more error. Okay, so that can be seen from this diagram also. If these 2 points they are nearby, then even lower amount of noise will increase the probability of making an error at the detector. Okay, so that is the thing, and the same can be reflected on BER versus SNR curve. Okay, so that is for 4 QAM and 16 QAM. So it is obvious that 16 QAM will have higher probability of error. Okay, so that is what we can see. And now when our environment is mobile, so not only there will be noise, but we will also have fading. Okay, so fading is nothing but we will have multiple paths because of reflection from maybe buildings or vehicles or even moving persons. Okay, so these reflectors, when it is moving elements, or the receiver itself is moving, okay, then these reflected paths they will superimposed in constructive or destructive manner. Okay, and since the position is changing, or the position of reflector is changing, in that case the resultant of whatever these multipaths, it will be changing in its strength. Okay, so received power level, it will be changing with respect to time, also it will be changing with respect to position. Okay, so whatever our signals are, they are now having random strength, as well as the phase will also be random. So random phase and random amplitude, that will be there in any of the received signal. Okay, so that is the fading. That is whenever there is momentarily change in received power. Okay, so that is a resultant effect of reflection, diffractions, and scattering from the obstacles. Okay, so now how we represent our received signal, right? So that received signal, it can be represented as R, that is equal to hx plus n. Fine. So our signal, that is R, is hx plus n. So this received signal, it is h, that is channel, that is this channel coefficient, that is because of fading, resultant of the effect of multipaths. X is our uh, transmitted signal, and n, that is the noise that is getting added. Okay, so this is how the signal constellation becomes, okay, when there is fading. So what we see, this black. Okay, so this is again for 8 psk only. Okay, so this in this we cannot differentiate how much noise, even if noise level is changing, then also we cannot differentiate between what is the effect of noise, how much is the noise. Okay, see, even when there is no noise, then also the signal constellation points, they are changing their positions, and this change in position, it is basically because of the h term, right? That is the channel response term, that is h. It will be a complex, right? Because of the phase shift in the signal, we represent it as in phase component and quadrature phase component. So if in phase and quadrature phase components, they are having different magnitudes, this phase change, it can be different in nature, right? So this, but how to deal with this is we can have certain phase correction in of the channel. Okay, so channel anyway, for getting correct detection, we need to estimate channel at the receiver, right? So when channel is estimated at the receiver, right, there may be different mechanisms like pilot transmission, that is known signal is transmitted from the transmitter, and we can estimate the channel based on what is received. Okay, so when this kind of phase correction of channel is done, and at that time we can at least get the constellation points at correct phase points. Okay, so this is how the constellation point of constellation diagram of received signals would look like when we do phase correction. Okay, so this is how our bit error rate would degrade when fading is there in the system. Okay, so what we can say is at 10 dB SNR in 4QAM, when there is only noise, the SNR is very much below 10 raised to minus, sorry, bit error rate is below 10 raised to minus 5. While if we consider this with fading, relay fading, so then at 10 dB, the bit error rate for 4QAM, it is quite higher than 10 raised to minus 2. Even it is more than 10 raised to minus 2. So that is this point, if we see, then it is around 0.025, somewhere around that, right? So this is we can see, look at the degradation, the extent of degradation that is made when fading is there. Okay, and again, one other thing that we observe is the slope of these curves. Okay, slopes of these BER curves. So if we see the rate of BER that is falling, that is quite high when fading is not there, and when there is fading, the bit error rate, it is almost it is dropping at the rate of 10 raised to minus 1, when there is improvement of 10 dB SNR, right? So that is there. So what can we do to improve this rate? Okay, so that is the diversity schemes. So diversity schemes is nothing but either transmitting or receiving multiple copies of the signals. Okay, so multiple copies of the signals, it can be received at the receiver in many ways. Okay, so the simplest way is adding more antennas at the receiver, right? So more antennas are added at the receiver, so that different paths, signals taking different paths would be received. And if different paths are received, so these antennas, they will face different fading coefficient. So what will happen is, if one antenna is receiving signal with worst fading conditions, another antenna may be receiving signal with better strength. So we can either process the strongest one, or we can combine whatever signals which are received at different antennas in certain combination form. Okay, so based on that, we can have we can have different diversity schemes, and they are polarization diversity, time or frequency diversity. So polarization diversity is sending signals at different polarizations. Okay, and time diversity is sending signal at different times. Okay, while frequency diversity, it is sending the same signal at different frequencies, and space diversity is using multiple antennas at the receiver. So these diversity schemes, they are selection combining, equal gain combining, multiple maximal ratio combining, or some switching diversities are there. And when we implement diversity, then the slope of BR versus SNR curve, it improves, and the slope, it will give us the diversity order. Okay, so if this diversity order that we can see when we look at the BER curves for different number of antennas. So this is for these curves are for 4 QAM in relay fading, and when we implement maximal ratio combining diversity. Okay, so here number of antennas equal to 1, 2, and 3. For these three uh, antenna combinations, the beta error rate versus SNR curves are shown, and we can see that the improvement in the slope, it is there for addition of every antenna at the receiver. Fine. Okay, so this is the comparison in of BR curves in AWGN, fading without diversity and fading with diversity. Okay, so that is what we can see. See, still we cannot reach this slope. Okay, so this slope, it is only into AWGN curve, right? So yes, with diversity we can get improvement in the rate at which beta error rate is falling with increase in SNR, but it is still less, or we can say that okay, for further improvement, we need to have large number of antennas at the receiver. Okay, so that consideration is there. But okay, see, we are getting diversity, or we go for higher order modulation scheme. What is happening is our improvement. Okay, so when we go for higher order modulation scheme, our beta error rate or error performance, it is degrading. So as a remedy of that, we go for diversity schemes. But still, even in diversity schemes, if we use higher order modulation schemes, will our error performance will get further degradation. That may not be helpful in actual communication schemes. And so there are trade-offs, that we cannot have as many number of antennas at the receiver as we want, or we cannot have as much higher order modulation scheme as that we want for our in increasing our the data rate or bandwidth efficiency or spectral efficiency. So what can we do for increasing our rate of transfer of information further? Okay, and that is this MIMO systems. Okay, so that is multiple input multiple output systems. Okay, and actually this MIMO systems takes into consideration of the fading. Okay, if there is fading, then MIMO systems would work. And it is observed that when there is rich scattering or fading is very much in the system, then actually if there are two parallel streams are transmitted, then it is possible to differentiate them at the receiver. Okay, so that is the known theory for MIMO systems. Okay, and then the channel capacity, that is considered as C is equal to bandwidth multiplied by log to 1 plus SNR. So we have two options where we can improve the capacity. That one is bandwidth and one is SNR, right? So bandwidth, even if we increase indefinitely, then our capacity will not improve in infinite, right? So there is a limitation on how much channel we can improve when our bandwidth is infinite. The reason behind this is, if bandwidth increases, our noise will increase, right? Because noise, it is additive white Gaussian noise, so noise is present at every frequency. So it is noise will be noise power spectral density multiplied by bandwidth. So that will be the total noise power. So we cannot increase capacity indefinitely with increasing our bandwidth. Okay, and power, that is again, we cannot increase the signal power, because most of our devices are mobile in nature, they are battery operated. So if we transmit more power, then battery, it will drain fast. We will see what happens when we transmit more power. Even more interference will also be there. So that we will discuss when we discuss what are the demands of future generation or current wireless technology. Okay, so bandwidth and power, it is difficult to increase. So MIMO systems, they are the systems which does a certain, which gives a certain kind of trade-off, okay, between power of transmission, or whether we want to use diversity or we want to use multiplexing. So we have multiple antennas at the transmitter. We can transmit parallel streams of data, so that we can get certain improvements. Okay, so how these MIMO systems can be implemented and they can be used. Okay, so at MIMO systems, we consider NT number of transmitting antennas. Let us say whatever is shown over here. So transmitter, it has NT number of antennas. At receiver, it has NR number of antennas. Okay, so now all these NT number of antennas, they can transmit simultaneously. Okay, when they transmit simultaneously, that is multiplexing. So that is a transmitter multiplexing. If they transmit different data, that is transmitter multiplexing. If they transmit same data, then it is transmitter diversity, right? So here in this transmitter, it can be used for both providing diversity gain or providing multiplexing gain. Okay, but both gains, it cannot be achieved simultaneously. So there is some diversity multiplexing trade-off. Okay, so how it can be how it can, how this MIMO system can be can achieve multiplexing, right? So multiplexing, that is through parallel transmission from all these three. Okay, so if we consider multiplexing 3 cross 3 MIMO system, okay, then it can be converted into parallel streams of 3 channels. Okay, so here it is something like some thing like it is 3 CISO systems, they are running in parallel. Okay, so then we can have diversity also. Okay, so diversity, that is all 3 antennas at the transmitter, they are transmitting the same symbol. Okay, so if same symbol is transmitted, these 3 antennas, they will receive 3 copies of signals from antenna 1, 3 copies of signals from antenna 2 of the transmitter, and 3 copies of signals from antenna 3 of the transmitter. Right, so in total, we can have 9 different paths through which the signals are reaching at the receiver, right? So probability of error, it will be of the error of SNR raised to -9, but that is not true in all the cases. Okay, that is not true because of diversity multiplexing trade-off. See, we cannot achieve full diversity, we cannot achieve full multiplexing. Okay, so something like this is what we can achieve. Okay, so where we can have some 1 or 2 different paths for multiplexing and certain paths for diversity. Okay, so this can be this is done by certainly using certain decompositions on MIMO channel. Okay, so sorry, so MIMO channel, so how it can be represented is, if we have different number of antennas, so we will have see 3 cross 3 3 system, we have 9 total paths, and all these 9 paths, they will have different gains, right? So now all 9 paths, they will have different gains, and these different gains can be represented into a matrix form, right? So that matrix, it will be of size nr cross nt, right? So that matrix, it will be representing different gains of different paths. Okay, uh, so that channel matrix, we need to do different decomposition. Okay, and different decomposition with certain precoding at the transmitter, we can have different multiplexing gain or different diversity gain, that how much we can get. Okay, so there is a trade-off. Okay, so that we are not discussing how this channel decomposition takes place and how precoding can be done. Okay, so we will now move into the second part. Okay, that is the uh, actual core idea of this talk. Okay, that is the candidate technologies for 5G and beyond. So in this we will discuss what are the technology demands for 5G, what would be 5G 4G specifications, and what actual technologies which are probable candidates for implementation into 5G. Okay, so we will quickly go through the demands of current wireless technology and in what ways it can be achieved. What are the 4G 5G specifications? We'll compare them. How much improvement are we planning through 5G, and which are the probable technology candidates that can be implemented at 5G level, that is massive MIMO and millimeter wave technology. And we will also see what spectrum efficient utilization schemes are there, and what schemes mechanisms we can implement for energy and expenditure reduction, right? Uh, so we'll see for wireless technology requirements. What are the requirements? Are minimum delay or minimum latency. Okay, so because see what we are doing right now, that is a real time application, right? See, I'm speaking at Chandigarh, and different centers at different locations are listening. That is the actual real time application for technology. But here not all connections are wireless, right? See, for example, this laptop that is connected through wireline up to certain locations. Okay, and then we may have certain wireless connections through which we all are we this presentation is getting broadcasted to different centers, right? So right now in this talk we will be focusing only wireless part of that. Okay, so if this wireless technology has to be implemented for real time applications. So for example, we do video conferencing through different platforms, like we have video call on WhatsApp. Okay, video conferencing through our Google Hangout. Okay, so these things, when we have on wireless medium, how we can minimize the delay, or what delay we are focusing. Okay, so and always high spectral efficiency or high data rates, this is required. That is because we have limited spectrum, right? The spectrum we cannot use infinite for any particular technology. Okay, so this in this spectrum efficiency we can improve, that is in different scenarios like noise limited, interference limited, and we always have a limited bandwidth. Okay, and we want to give higher bandwidth per user. Okay, so higher bandwidth per user, how can we give? That is that will be the actual uh, topic for the next session. Okay, so that also we will see. So what are the limitations for our uh, for those demands that wireless technology is uh, having with us? So we have some limitations at physical layer. So those limitations are the available spectrum that is available, that is very much limited. And we have EM wave propagation principles. So EM wave, it has certain attenuation, certain propagation models. They cannot have different frequencies. They have different propagation models. Not all frequencies would scatter with same limit. Okay, and we have finally information theoretic limits. So information theory, it says that infinite data cannot be transmitted in a given bandwidth. So how to overcome these limits? Okay, that is the challenge. And we have to have efficient wireless networks. So efficient wireless networks, how do we get? So some of the proposals, they are densely deployed access points. Okay, so that is actually dense cells or small cell networks, picocell networks, Okay, so reducing cell size, how it will help, and what would be the limitations, right? So we don't have large spectrum, but we want to give large bandwidth to every user. Okay, so large bandwidth when we give to every user, then we can actually use the limited spectrum for higher data rate per user, right? So, and improving spectral efficiency. So with MIMO technology, we can achieve these demands, and with these limitations up to certain level. Okay, so MIMO technology, we have point to point MIMO, multi-user MIMO, and massive MIMO, right? So point to point MIMO, it will be actually useful when we want to connect base station to base station, right? While multi-user MIMO and massive MIMO, these are somewhat related terms, right? So they are uh, proposed for implementation when we want to cater multiple number of users through single access point. So single access point, by that one can mean a base station when it is cellular systems. Okay, fine. So this higher data rates or higher channel capacity, that is the demand, and that demand, when we consider in noise limited scenarios, how it can be achieved, that is increasing transmitted signal power. Up to what level we can achieve it, that is a different thing, but increasing transmitted signal power, that is not the best solution. Okay, and that is why it is given in red, right? So red means danger. Okay, so if you increase signal power, there would be certain dangers, okay, that we will discuss. Increasing bandwidth, okay, if we increase the bandwidth, noise power is also increasing. Okay, but anyway, if we have to transmit more data, bandwidth has to be increased, that is the ultimate solution. But how to take care of this noise power? Okay, so noise power is more, that means our SNR would degrade. Okay, so we'll see how MIMO systems gets us to less effect of this noise. Okay, so what we can have as other solutions is reduce distance. Okay, if we reduce distance, sorry, if we reduce distance, we will have less attenuation. Okay, less attenuation in the sense, up to less distance our signal will get attenuated less, but it has different limitations, so that we will see. Receive antenna diversity, of course this is a solution. Receive antenna diversity is a very good solution. Multiple transmitter antennas, so through transmitter antennas, okay, we can have beamforming. So beamforming, it will actually give us array pattern, right? So array gain, that will have large gain uh, towards the user, right? So user will receive more power. Okay, and we have multiplexing gain, right? So multiplexing, that will actually that is transmitting parallel streams of data, and parallel streams of data actually gives high data rates, right? And the other, since it is noise limited, we want to reduce noise, so we can have RF design that improves noise figure, and that is at the hardware level. Okay, so then when it is interference, right? So in interference, if we transmit more power, right, that means more interference will be there, right? So because if more power is transmitted, more stronger signals will reach to the next cells. Okay, so that is one more limitation. And again, if we reduce cell sizes, okay, when we have reduced the cell sizes, then we will have less number of users per cell. Okay, and then if we have less number of users, if we see each user as an interferer, then less number of interference within the cell. Okay, but if with this reduction of cell size, if we are not reducing the transmitted power in the proportionate manner, then the interference in the neighboring cells, that would also be increasing. Okay, so that it is not a single variable, but it will be a kind of multiple variable optimization kind of thing. Okay, so multiple variables will put trade-off on how much reduction can we get, how much signal power we have to transmit, how much bandwidth we have to allocate. Okay, so of course this receive antenna diversity, multiple transmitters, that is always a solution. But with this, we have one more solution is special processing through smart antennas. Okay, so smart antennas, that is, it can change its radiation pattern according to need. Okay, so with once the signal that is incoming, direction of arrival is known, the useful signal at what direction it is coming, interference at what direction it is coming, based on that antenna radiation pattern, nulls of that, and the maximum gain point of that, that can be uh, selected. Okay, so that is through smart antennas. Okay, so now if we have limited bandwidth, okay, so performance, uh, how we can improve, that is higher order modulation. But then higher order modulation, it will degrade our performance. Okay, so that performance degradation, it can be taken care with receive antenna diversity or transmit antenna diversity, right? But with that, if we have given certain modulation scheme, and within that if we have to improve our data rate, then multiplexed transmission is a solution. Okay, so multiplexed transmission, it is available only with MIMO systems, right? So at least at base station, we need multiple antennas. Okay, so that is where we have multiple antenna systems into place. Okay, so here the actual 4G systems, what are the specifications? Okay, the standard is LTE or LTE advanced. That is where we are going. Okay, and this is already implemented. Okay, so which modulation scheme and multiple access schemes? So we have OFDM, that is orthogonal frequency division multiplexing, and for multiple access it is OFDM A, right? So that is orthogonal frequency division multiple access. Okay, so OFDM, when it is multiplexing, then we transmit uh, same users data at different subcarriers. Okay, so that uh, while in multiple access, different subcarriers carries different users data. Okay, so that is multiple access and multiplexing. Okay, and QAM up to 64 QAM, that is used in LTE standards. Okay, so MIMO systems up to 8 cross 8 is acceptable in 4G specifications, and speeds up to 300 Mbps wireless connectivity when hotspot is at hotspot level. Okay, and channel bandwidth up to 20 megahertz, while duplexing, that is TDD or FTD, is possible. Okay, so duplexing is when a call is being connected, so I have to speak as well as I have to listen. Okay, so so sending data as well as receiving data, how do we do? So that is through time division duplexing or through frequency division duplexing. So we will see what this TDD and FDD is. Okay, and latency, that is less than 100 millisecond. Okay, so that is when the device is idle. From idle to active transition mode, this latency less than 100 millisecond is targeted, otherwise less than 10 millisecond is targeted. Okay, so latency is in what time our calls get connected and transmission, actual transmission reception takes place. Okay, so this 4G specifications and 5G specifications, what are targeted? Okay, so different terms that can be targeted, they are peak data rate. Okay, so peak data rate, that that is targeted is 10 Gbps, for mobiles 20 Gbps. Okay, that is under special conditions. Okay, so that is under idealized conditions. Okay, so user experience data rate. Okay, so user experience data rate, it will be 100 mbps. Okay, so user experience data rate, it is different than this hotspot data rate, right? Because hotspot, it will be connected to many users, right? So that is 1 gbps is targeted. Okay, So latency, that is radio communication from send and receive. Okay, so what is the total delay? Okay, so delay in this call getting connected and communication happening. So that will be around 1 millisecond is targeted. And mobility, so with moving receivers, okay, actually while traveling, how much speed is acceptable, while connection density, that is how many devices we can have in a certain given area. Okay, and energy efficiency, that is network bits per joule, how many bits per joule we can transmit, or how many uh, and we have sorry, spectrum efficiency, that is per bandwidth, how many bits we can transmit per unit of bandwidth, how many bits we can transmit. And area traffic is how many bits per second per unit area we can have, right? So these specifications we can compare with 4G and 5G specifications. Okay, so this in internal area, okay, so inner area, that is IMT advanced, that has given specifications for 4G, and outer, that is IMT 2020, that are the specifications for 5G. So how much improvement we are targeting? So 3 times improvement as compared to 4G is targeted in spectrum efficiency. If we see user experienced data rate, we are targeting 100 times. Peak data rate, we are targeting 20 times of those that targeted in 4G. Area traffic capacity, we are targeting 10 times. Network energy efficiency, we are targeting 100 times. Connection density, we are targeting 10 raised to 6 now, that is uh, yeah, 10 raised to 5 and 10 raised to 6, so that is 10 times of that. Okay, and latency, that is again 10 millisecond, 1 millisecond, so that also is 10 times. Okay, fine. So mobility, that was 350 kilometer per hour in 4G, that is targeted is 500 kilometer per second in 5G. Okay, so that is the specification level, how much improvement we are targeting from as compared to 4G into 5G. Okay, so this data, it is available on this ITU website on this link. Okay, so how these targets can be achieved, what are probable solutions we have at physical as well as make layer. So we will be considering only physical layer at this moment. Okay, so what different blocks we can see. Okay, so these are the blocks at which we can have implementation of different technologies. So we have these spectrums of centimeter wave or millimeter wave. Okay, so up to 30 gigahertz or up to 100 gigahertz, actually it is 300 gigahertz, but in principle we have opened only up to 100 gigahertz. Okay, so let us see, 6 gigahertz band can be used, 28 gigahertz band can be used, or 86 gigahertz band can be used. So these bands are actually made free by this FCC, that is Federal Communications Commission. So that gives this frequency bands for experimentation to 5G related systems. Okay, so now that is which spectrum we can use. Okay, so spectrum level, whether we can use centimeter waves or millimeter waves. Okay, at waveform level, so waveform level, what kind of technologies we can use, which so this also deals with somewhat, it has also somewhat connection with modulation scheme. Okay, so modulation scheme and waveform, they go side by side. Okay, and multiple access scheme, so which multiple access schemes can be used? Shall it be similar to those used in 4G, or they can be somewhat different? So we can have different as OFDMA, so that is single carrier FDMA, non-orthogonal multiple access, SCMA or RSMA. So different multiple access schemes are there, which out of this non-orthogonal multiple access has been widely accepted for 5G applications, and most probably this is going to get standardized for 5G systems. So this we will discuss in detail in the next session, but this time we are more focusing towards this part, that is MIMO part. Which kind of MIMO technology can we use for actual connection? Okay, so that is what will be the enabling technology for 5G. Okay, so uh, and so going towards that, what 5G technology candidates are there? Okay, so enabling technology, that will be the basic block. Okay, or we can say that that is something like uh, something like the technology which actually gives the physical connection between transmitter and receiver. So by physical connection, that means the air interface. Okay, how the air interface gets connected. Okay, so that enabling technologies, that may be massive MIMO or millimeter wave MIMO. Okay, so what technology shall we implement, and what is the idea behind that? Okay, so in conjunction of massive MIMO with millimeter wave spectrum. Okay, that is the massive millimeter wave massive MIMO. Okay, so that is the basic idea, which is widely expressed, that probably this would be the standardized technology. Okay, while we shall have, since we are uh, improving spectrum efficiency, so we shall have certain spectrum efficient technologies have to be used. Okay, so some of them we will use, some energy saving mechanisms we will be using, some uh, uh, capex and opex, that is capital expenditure and operational expenditure. Okay, so that has to be reduced. This is the main interest of the service providers, right? So service providers, they actually get profit if capital expenditure and operational expenditure is less, right? In terms of money they are talking, right? Because they have to make a business and earn profit. So this capital expenditure and operational expenditure, that is the main interest of the service providers. Okay, and of course multiple access technologies which we can take for serving multiple users. Okay, so large MIMO systems, which are termed as number of antennas, that is greater than 10 at both transmitter and receivers. But now this greater than 10 is no longer valid, because actually we are talking about massive MIMO systems, and which can have hundreds and thousands of antennas. Okay, and again with millimeter wave technologies, the antenna spacing and antenna dimension, this has to be very small. So we can in fact have more number of antennas within very small area also. So within our next generation mobile phones, we can have hundreds of antennas actually in place. Okay, so if it is millimeter wave technology or terahertz technology, we can have hundreds of antennas with our mobile handset itself. Okay, so that means we will no longer be limiting up to 8 antennas which are supported by 4G technology. Okay, okay. So this advantages with large MIMO systems, that is more data rates, that is if we have more number of antennas, obviously we will have more number of parallel data transmissions would have been possible. So uh, higher rates can be achieved. The other thing is improved average SNR. See, this improved average SNR, it will be mainly because of the array gain of the antennas. Okay, see, signal getting received with one antenna and signal getting received with multiple antennas. So we can look at the improved average SNR in the form of beamforming also. Okay, see, beamforming, that is actually uh, confirming, limiting the transmitted power only up to certain limit, right? So only up to certain range of the beam, right? So that is, when we use large number of antennas, we can have improved average SNR, and we also get channel hardening effect. So channel hardening effect is nothing but we get off diagonal elements of H Hermitian as zeros. Okay, so that means the channel actually it becomes somewhat determinant. Okay, although we have large number of channel coefficients, with that if we do this H Hermitian kind of operation, we can have uh, this H Hermitian matrix that we get. It would have only diagonal elements as non-zero elements, and that actually helps in decomposing our MIMO channel into parallel transmissions. Okay, so we get huge multiplexing gain with this channel hardening effect. Okay, and with improved SNR, we can have suboptimal detection also. So detection complexity we can reduce with suboptimal detection. Okay, and usefulness, that means where these large MIMO systems can be used. Okay, so that is mainly at fixed terminals, because if we consider hundreds and thousands of antennas, okay, with that, if we consider that many number of RF chains, then the system will be really bulky. Okay, so we say that okay, mobile phones they can have 100 antennas, but having 100 RF chains, that would be quite difficult. Okay, so we still will be okay when we go towards massive MIMO system in a short while, we will see why mobile phones they are still they can be still limited to certain number of antennas, and we can still get a better performance. Okay, so when the fixed terminals are there, we can implement large number of antennas. So that is maybe as base stations or Wi-Fi access points. Okay, so something like that. And so going into multi-user MIMO systems. Okay, so what we see is large number of antennas can be acceptable at only one end, right? That is fixed end. So we can see that okay, multiple antennas actually can be implemented at base station, and users they can be having single antenna or maybe multiple antennas, but not as large as number of antennas at the base station. Okay, so with that, how transmission and reception can take place? See, this multiple user MIMO system. Okay, so MIMO in uplink, all the users they can transmit data simultaneously or in time division mode. Okay, so or they can do TDMA also. Okay, so if they are using this base station, it is not capable of differentiating signals which are transmitted at same time from all users. In that case, time division multiplexing has to be done, right? So user 1 transmitting at certain time, user 2 will transmit at different time, but this transmitting at different times will not help much because it is taking time resource. Okay, it is dividing time resource. Okay, but what we want is all the time, all the frequency should be used by all the users. Okay, so that is what our idea is. Okay, so while in downlink base station, it will broadcast the all the users data. Okay, and all users can get the data. Okay, so what challenges are when users are simultaneously sending data to base station in uplink? So uplink synchronization, that is challenging. Okay, and these users, even though they are synchronized and they are located at different geographical locations, then the signals that are reaching receiver, that will be delayed in certain although it will be small time, but the delay will be there in different signals. So base station will still see that the signal is not synchronized. Okay, so that is there, and if the synchronization is lost, then different users will see different interference from the other users. Okay, so that is inter-user interference. Okay, so it is something like it is not asynchronous transmission from all users. Okay, so what will happen is one user is transmitting, user 2 that is not transmitting, or it is receiving. So that means user 1's data will be getting received at user 2 when it is receiving data, right? So that is an interference for user 2, which is not acceptable. We shall see certain mechanisms for not having such interference. Okay, so that is certain challenges that are still existing in multiple user MIMO systems. Okay, right. So then what we have is massive MIMO systems. Okay, so massive MIMO, that also is very much similar to multiple user MIMO, but in multiple user MIMO, the number of antennas at base station, they can be comparable to the number of users. Okay, while in massive MIMO, number of antennas at the base station has to be very large as compared to number of users. Okay, so here uh, we can have two kinds of mechanisms for serving these multiple users. Okay, so one is as shown over here, that different beams are generated for different users. Okay, so that is possible in line of sight. Okay, so massive MIMO, what it is it is scalable version of multi-user MIMO. So multi-user MIMO, the complexity in multi-user MIMO, the complexity is not a linear function of number of users or number of antennas at transmitter. Okay, so scalable version, that means the complexity, it becomes a linear function of either a number of users or number of transmitting antennas or number of antennas at the base station. Okay, so that is scalability in this sense. So massive MIMO, they are scalable. Okay, so even if users or antennas are increasing, then also not much increase in complexity will be there. Okay, so these different basic differences are: only base station knows the channel state information, users, they don't need channel state information, and number of antennas at base station, it is very large as to number of users. That is what already we have seen, and simple linear processing can be used. Okay, or it has to be used, so that complexity is not much. Okay, so in this transmission, it can take place that uplink. The base station, it has to recover individual signals that can be transmitted from multiple users. Okay, so that is why uplink, it needs the channel state information. While in downlink, the base station, it has to ensure that each of the terminal receives only the signal that is intended for it. Okay, so downlink, the channel state information, it is not required at the user level. Okay, that is because this base station, it will take care of whatever recording has to be done, or whatever pre-processing has to be done on the data, so that the user doesn't need channel state information while decoding it. Okay, so that means LOS, when it is line of sight, base station will do beam forming. So beam forming, when it is beam forming, when it is line of sight, then we assume that, okay, channel, there is no fading, right? So when it is line of sight, fading doesn't come into picture, only the delay in the channel, right? So similarly, when there is non line of sight, then this base station, it will transmit the signal such that all the signals get constructively added at the terminal. So how it is done, we will see, we will understand it better. Okay, so since there are large number of antennas, we can have narrower beams and high spectral efficiencies. Okay, so narrower beams, if we have multiple narrow beams, then we can transmit multiple users data into those multiple beams, so that multiple frequency channels are not required for different users. Okay. Yeah. So here again, the uplink and downlink data transmission, it is very much similar to that we have seen in multi-user MIMO, right? So that is there. We have line of sight and non-line of sight strategies for massive MIMO. So that we have seen, when it is line of sight, it generates multiple beams. Okay, the base station, it generates multiple beams over which information can be transmitted simultaneously. Okay, while if it is not line of sight, okay, see, although no obstacle is shown in this figure between the base station and the user, but we assume that, okay, there is certain obstacle, and user and base station, they are not in line of sight. Okay, so here the base station, it will transmit the signal in such a way that when these two paths, okay, these two paths which are shown over here, when these signals from these two paths are added, they gets added in phase. Okay, when they get added in phase, that means they are constructively added. Okay, so it looks like there is no fading at all, right? So all the signals, all the multipath components, if they are getting added at the user point, okay, then we see that, okay, we consider it as no fading is there, right? So ultimately channel state informations, they are not required. Okay, so this is also a kind of we can consider a kind of beam forming only. Okay, but this is a beam forming which is considering non line of sight kind of scenario, right? So it is transmitting the signals so that the user, it gets maximum benefit of multi-user scenario, right? So that is taken care by base station.